Earthquakes are huge natural disasters that have lots of impact on life and property. In some places, the average number of earthquakes per year is almost one per day. Is there any way to prevent this? Turns out not. This is Mother Nature's way of showing anger, unlike human actions. So, what can we possibly do? We can predict the possibility of earthquakes and take precautionary measures because that's going to save a lot of life and also property. Hi, I'm Vignesh,
And I'm Chester.
and our goal is to build a machine learning model to predict the possibility of an earthquake. So to build our machine learning model, we use the simulated dataset by Los Alamos National Laboratory. So they use seismic sensors, which is basically piezoceramic sensors that detect voltages whenever they are experiencing a seismic wave. And as you can see from the graph, the red signal represents the seismic voltages. And the blue represents the time to failure, which is nothing but the time remaining till the next earthquake. So whenever the blue signal goes down to zero, that means there's been an earthquake. So as you can see from this graph, there are a lot of analogies to like audio signal processing. So in our entire project, we will be focusing on exploring audio related techniques for in both machine learning space and also in the deep learning space to solve this problem.
To reiterate, we formulate our task as a regression problem. At each time step, we want to predict the time to failure of an earthquake, seconds, given the preceding seismic waveform, a sequence of integer valued voltages. Now I'll briefly review the flow for our process. The input to our pipeline is raw, noisy seismic signal. We then transform this signal into its frequency domain via a short time Fourier transform. We then operate on the spectrogram with a denoising algorithm, robust PCA, to produce a denoised seismic signal. We then operate on this denoised seismic signal, producing a variety of features, including analytically derived statistical features and also features learned intrinsically from the data. We can then do prediction on these features. The first step in our pipeline is to denoise the noisy seismic signal. We do this via a robust PCA algorithm. To demonstrate the denoising process, we can listen to a downsampled version of the noisy signal and the resulting clean signal after applying robust PCA. As mentioned before, given the denoise signal, we then compute a variety of different features to represent earthquakes. Of particular note are two feature learning algorithms we applied. One is based on a spectral embedding of an MFCC representation of earthquakes. The other is based on a linear embedding of the raw signal. Here, individual points represent individual earthquakes, and lighter points correspond to earthquake segments with a lower time to failure. In both graphs, we see that the embeddings exhibit clear cluster structure. In a spectral embedding of earthquakes, nearby points correspond to regions of high connectivity in a weighted graph representation of the data, where weights correspond to similarity. In a linear MDS embedding of the raw signal, nearby points correspond to points that are nearby in Euclidean space. The cluster structure we observed here motivates us to leverage these learned features for prediction. To do prediction, given the earthquake features mentioned previously, we applied a variety of different algorithms and report the mean absolute error on our five-fold cross-validation experiments. We also report the normalized sparsity, which roughly corresponds to the efficiency of inference for a particular algorithm. Additionally, the top 5 algorithms utilize statistical and MFCC features computed from the data, while the bottom 2 algorithms utilize learned features. Next, Vignesh will describe a deep learning-based approach to doing both feature learning and prediction.
One of our deep learning methods is by using WaveNet as a form of dimensionality reduction. The true data is of like 150,000 time steps in length. So in order to reduce that, we use dilated causal convolutions to reduce the amount like just 150 time steps. And then we use a LSTM on top of that 150 time step to predict the time to failure. This gives a mean absolute error of 1.8. So to summarize, we propose an audio-based approach of using seismic activity to predict the possibility of an earthquake. We do hope in the future lots of such approaches come into the picture to help save a lot of life and property. Thank you.